was born. Trust you're fine. Myself, I'm fine. A member of Group 18, Computer Architecture. We'll be taking you through a topic titled Speeding the Address Translation. But before we go to speeding the address translation, we must know what an address translation is. So, primarily, an address translation is a process used in computer systems, especially in the context of memory management and computer architecture. It involves translating virtual addresses into physical addresses. In this slide, we would have insight on how the address translation works, since it's based on virtual addresses and physical addresses. Taking virtual addresses. In modern computer systems, applications often deal with virtual memory addresses. These addresses are generated by the program and do not correspond directly to physical locations in the computer's RAM. Come to the physical addresses, also known as the physical memory, which is the RAM, is where actual data is stored. Each byte in physical memory has a unique physical address. Memory Management Unit. So the MMU is a hardware component that performs address translation. It takes the virtual memory address generated by a program and translates it into a corresponding physical memory address. Translation table. The MMU uses a translation table or page table to perform this translation. The table maps virtual addresses to physical addresses. When the CPU access memory, the MMU consults this table to find the corresponding physical address. So address translation is a crucial part of modern computer systems because it allows for the efficient use of memory and enables features like virtual memory, where programs can use more memory than physically available by swapping data in and out of RAM and secondary storage like a hard drive. It also provides memory protection as the MMU can prevent unauthorized access to certain memory regions. So now we come to our main topic, which is the speeding up address translation. Address translation, especially in the context of virtual memory systems, is an essential part of modern computer architecture. Speeding up address translation involves optimizing the translation process to reduce latency and improve system performance. Here are some ways to speed up address translation. But before we look at the ways to speed up address translation, you must first know some importance of address translation or speeding up address translation. So, speeding up address translation in computer systems is crucial for several reasons as it directly impacts system performance, efficiency, and user experience. Here are some of the key reasons why speeding up address translation is important. So, the overall system performance. Address translation is a fundamental operation that occurs in virtually every memory access. Faster address translation leads to faster program execution and improved overall system performance. It helps applications run more smoothly and efficiently. So speeding up address translation reduces what latency. Faster address translation reduces the latency between when the program requests data from memory and when that data is actually accessed. Low latency memory access is critical for real-time applications such as video games and multimedia streaming. Efficient use of hardware. Speeding up address translation allows for better utilization of hardware resources. When address translation is slow, the CPU may spend more time waiting for memory access, leading to underutilization of processing power. Energy efficiency. Faster address translation can lead to energy savings in portable devices and data centers. When processors can perform tasks more quickly, they can enter low power states sooner, reducing energy consumption. Scalability. Fast address translation is especially important in systems with large memory spaces, such as servers and supercomputers. It enables efficient scaling of memory management to handle increasing workloads. In conclusion, speeding Speeding up address translation is a critical optimization in computer system that has wide-ranging implications for performance, efficiency, and user experience. Address translation, the process of mapping virtual addresses to physical addresses, impacts how quickly programs can access data and execute tasks. So we've already known that speeding up address translation improves performance. So it reduces memory access latency, allowing applications to run more efficiently and responsively.
Okay, my name is Zakaria Omar, BSc Software Engineering, Group C, and I'll be continuing from where my colleague ended. My topic for discussion is implementing protection with virtual memory. I've highlighted some of the points we'll be talking about under this topic given. What is a virtual memory? Types of virtual memory, functions of virtual memory. Then we'll delve down to the main topic for discussion, how to implement protection with virtual memory. What is a virtual memory? Virtual memory uses both hardware and software to enable a computer compensate for physical memory shortages, temporarily transferring data from random access memory, which is the RAM, to disk storage. Mapping chunks of memory to disk files enables a computer to treat secondary memory as though it were the main memory. I'll explain this point with the second point. Today, most personal computers, which is PCs, come with at least 8 gigabytes of RAM, but sometimes this is not enough to run several programs at one time. This is where the virtual memory comes in. Virtual memory frees up RAM by swapping data that has not been used recently over to a storage device such as a hard drive or a solid state drive, which is the SSD. Move on to types of virtual memory. There are two types of virtual memory. They are paging and segmenting or segmentation. The paging is a virtual memory technique that separates memory into sections called paging files. And segmentation is another method of managing virtual memory. I'll explain further when we get to the points where we are showing how to implement protection with virtual memory. We then move ahead to the functions of virtual memory. 1. Space allocation. 2. Program relocation. 3. Program execution. 4. Code sharing. All these functions stated serve one purpose, which is the main function of the virtual memory is that it provides virtual address mapping between applications and hardware memory. Virtual memory provides many functions, including multitasking, that is multiple tasks executing at once on one CPU, allowing multiple processes to access the same shared library in memory, swapping, and others. Let's move to the next slide. Now we'll delve down to the main topic for discussion, which is implementing protection with virtual memory. Here, I'll explain to you how the types of virtual memory helps in implementing the protection with virtual memory. So let's move to the slides. When implementing protection with virtual memory, we can use techniques like memory segmentation and paging. These help ensure that each process has its own protected memory space, preventing unauthorized access and improving security. How memory segmentation works in implementing protection with virtual memory. Memory segmentation divides virtual addresses space into segments. As the word goes, segmentation. It divides it into sets, each representing a specific type of data or code. So this set represents a specific data type or code. Each segment has its own access permissions. Each of the segments to have their own access permissions, such as read, write, or execute. This allows for fine-grained control over memory access and protection. The reason why they do this is to make the protection clear, to be able to access every data in the system, in the memory, so that like they can control, they can have control over every memory and protect every memory accordingly. Now let's move to the next one. How paging contributes to implementing protection with virtual memory. Paging contributes to virtual memory by the virtual address space and the physical memory into fixed size. Let me take that again. Paging contributes to memory by dividing the virtual address space and physical memory into fixed size pages. Each page has its own access permissions, allowing for granular control over memory protection. It helps prevent unauthorized memory by assigning appropriate permissions to each page. Now I'll state to you how the protection itself is done. Protection is implemented with virtual memory by assigning permissions to different memory pages. This ensures the process can only access memory they are authorized to, enhancing and preventing unauthorized access. So the main aim of protection, implementing the protection, is to protect the memory or the data from unauthorized access. Like no one can just go into your system and just find this kind of information. That's why the protection is implemented. I hope this will help you in a way to understand implementing protection with virtual memory. Thank you.
Good day, guys. My name is Olamide, and I'll be taking you through multi-level paging and segmentation. Multi-level paging is an extension of the traditional paging memory management scheme. In other words, an additional level of hierarchy to the page table structure to improve memory management efficiency. In other words, multi-level paging increases the efficiency of memory management. How it works. Instead of having a single flat page table, multi-level paging divides the page table into multiple levels, creating a tree-like structure. The top level page table points to the second level page tables, and those in turn points to the actual page frames. This hierarchical structure reduces the size of each page table and speeds up memory access by reducing the number of entries that must be searched to find a particular memory location. We have some advantages of multi-level paging, and these are: one, efficiency in memory utilization. Now, only the parts of the page table that are needed are loaded into the memory. So it means it reduces the size of the memory, leaving the important parts to be stored in the memory. Number two, reduced page table size. Each level has fewer entries, therefore saving memory. Number three, improved performance. It makes the access times faster due to the hierarchical structure of the multi-level paging. Use cases. Multi-level paging is used in modern operating systems to manage large address spaces efficiently. Now we are moving on to segmentation. Segmentation is another memory management technique that divides the physical memory into logical segments, each representing a different type of data or code. These segments can vary in size and can be dynamically allocated as seen in the diagrams above. We can see there are logical There is a logical view of segmentation in the diagrams above, and each is divided, or each has been allocated with different colors, which makes it easy for identification. And now we have a table down there too, which has the segment number, base address, and limits. So you can see from segment number 0, the base address is 500 and the limit is 600. And at segment number 1, The base address is 2500 and the limit is 800. Segment number 2, we can see the base address is 1500 and the limit is 400. Segment number 3, we can see the base address is 4600 and the limit is 200. Base address with 3800, that segment number 4 has a limit of 400, and this can be known, or it's called, the segment table. How the segmentation works. In segmentation, a process's address space is divided into logical segments such as code, data, stack, and heap. Each segment can grow or shrink independently as the program runs. Segmentation uses segment tables to map logical addresses to physical addresses, allowing for flexible memory allocation. Advantages of segmentation. In segmentation, a process's address space is divided into logical segments such as code, data, stack, and heap. Each segment can grow or shrink independently as the program runs. Segmentation uses segment tables to map logical addresses to physical addresses, allowing for flexible memory allocation. Use cases. Segmentation is commonly used in programming languages such as C and C++ to manage memory allocation and protection. In summary, multi-level paging improves memory management efficiency by using hierarchical structure, while segmentation offers flexibility and logical organization of memory by dividing it into segments. Yeah. The choice between these techniques depends on the requirements of the operating system or application. Thank you very much, and this is the end of my part.
Hello guys, my name is Richmond Nelson and I'm in group 18. I'm here to talk about cache in virtual memory system. So please let's begin. When we talk about virtual memory, it's a memory management technique in which every process operates in its own address space under the assumption that it has the entire address space to itself. Let's come to virtual address. Virtual address requires translation into a physical address to actually accept the system memory. Virtual memory maps program addresses into RAM addresses. If no more space is available, these addresses will be mapped into the disk as shown there. Now let's come to cache. What's cache? Cache memory is a faster and smaller segment of memory whose access time is as close registers. It can be accessed more quickly than the original. Cache are mostly good when the frequent keys is enough and the infrequent keys is not too expensive. Caching ensures locality in two ways. Temporal time, which is keeping recent access data items saved, and spatial space, since we often bring in contiguous blocks of data to the cache upon a cache mess. The purpose of cache memory is to reduce the amount of time needed to access data from the storage or external source, such as disk or networks. Programs can run more quickly since they don't have to wait for slower components like hard drives or network connections every time they need something new. Caching improves system performance by providing quick access to frequent use data and instructions. Make the process of reading data faster. Virtual memory can use cache memory. Since physical caches don't guarantee a fast process, we use virtual caches. CPU is directly connected to the cache and it looks up the virtual addresses in it while avoiding translations. Translations will occur only if an address isn't found. Eventually, Each program has its own virtual cache. Well, there are differences between cache memory and virtual. Here are some differences between virtual memory and cache memory. 1. Virtual memory extends the capacity of the main memory for the user, whilst cache memory fastens the data accessing speed of CPU. 2. Virtual memory is technique, whilst cache memory is a storage unit. 3. Virtual memory allows execution of the program that is larger than the main memory, whilst cache memory stores the copy of the original data that has been recently used. 4. Virtual memory is managed by the operating system, whilst cache memory is fully managed by the hardware. 5. Virtual memory is far larger than cached memory, whilst cache memory has bounded size. 6. Virtual memory requires mapping structures to map virtual addresses to physical address. In cache memory, there is no mapping structures are required as such in a cached memory. In all, to make the process of reading data faster, virtual memory can use cache memory. Since physical caches don't guarantee the fast process, we use virtual caches. The CPU is directly connected to the cache and it looks up the virtual. Thank you.